We've now got David Bowman, G0MRF, going to talk about one of our projects that's going on within AMSAT-UK and the FUNcube team, of which I'm a member. It's going to be an exciting time over the next year or so with launch. Well, we'll talk about launches later, won't we? But there are a lot of satellites in design and build at the moment. Over to David.
All right, very good morning. Thank you very much for not being downstairs in the extremely crowded Lucy Green room. I went down there earlier and everyone is literally packed in like sardines, so thank you for showing up here today. I'm going to talk about two projects which are actively running with AMSAT-UK at the moment. The first is FUNcube Plus, which is a project that we've sort of had on the back burner for the last couple of years or so. It's a 2U CubeSat, which is essentially a follow-on to our AO-73 mission, which celebrates its 12th birthday in space in about a month's time. So this 2U project is something we've been planning and is now coming along reasonably nicely. And we're also going to look at a 6U educational satellite called JOVIAN-1 that's currently under construction at the University of Surrey. And we have a payload on that satellite. So I'll start off with FUNcube Plus and have a little look at that, and then a little more of a look at our payload on JOVIAN-1, and that's what we call FUNcube Lite. First of all, before you get too excited with all of that talk from Martin Sweeting about exploring space in 50 years, JOVIAN-1, despite its name, is not going anywhere near the planet Jupiter, so definitely a low Earth orbit. So let's start off with this 2U CubeSat mission then. As I say, it's a follow-on mission to AO-73. AO-73 is doing quite well. Started off at 630 kilometers, and it's now slowly coming down through the 8,000 Starlink satellites at about 575, 580. Still operational in transponder mode, but the batteries, after 11 years, are showing signs of some degradation, so a follow-on mission is quite appropriate. We've called it FUNcube Plus because it's basically the same specification as our original satellite, but with some additional features. It'll still have a UV linear transponder with 1200 bits per second BPSK, as we see on AO-73. We use the BPSK for educational outreach, as well as looking at the satellite's health. We're going to install a LV-FM transponder, which is 1261 megahertz or so uplink. That uplink's been chosen to fit in with the recent changes in the band plan to 23 centimeters across Europe mainly. I think our government isn't going to implement that yet, but we've put the frequency in the new sort of recommended allocation there. We're going to include a camera for still images. And along with that, we're going to send those down on a QSPA downlink, which is about 18 kilohertz wide on the VHF band. It's not high-speed data as you would as defined, but it will enable us to build up pictures over a number of orbits. And the pictures are going to be broken up into about 128 or so segments. Each one will be downloaded, identified by your software, and put in a particular part of the image that's reconstructed on your PC. We also need to put some attitude stabilization. I won't say 3-axis control on this satellite, but we'll do need to correct some of the aspects of stabilization that are lacking on AO-73. AO-73, its attitude stabilization is a rare earth magnet sitting in the middle, so it follows the Earth's magnetic field around. That keeps it reasonably stable in in 2 axes. But it is rotating around that magnetic moment at around once every 4 seconds at the moment. It's been up to about 1 rotation every 2 seconds, none of which is compatible with running a camera on board, so we have to do something about that. So although this is running in the background and it's not our immediate priority, whereabouts are we on this? Well, as you can see, that we've had a number of bits of flight hardware turning up in the UK. We have purchased or acquired from ISIS-Space in the Netherlands a 2U CubeSat structure, an IMTQ, which is a magnetorquer board for the attitude stabilization. We've got 2 electrical power systems, one for development, because we haven't used that piece of electronics from ISIS-Space before, and one for flight. They use the very popular 18650 lithium-ion cells. They're very, very reliable. We use those on AO73, and it gives about 8.3 volts or so for the supply line when we wire those in series. An antenna deployment system for UHF and VHF, 2 dipoles deployed, one on each band. And at the moment we have 4 solar panels. We've got 1 more being manufactured in the Netherlands. And for those of you who are really good with cubes, you'll notice that's 1 short of a full set. And of course, that remaining panel is going to have the camera and a deployable antenna on it for 23 SEMS. I would like to say thank you to a few people, Keith, Graham, and Wouter, let's say for logistics, making all this stuff appear fairly painlessly in West London. And that's hopefully going to be all assembled here and then shipped out for launch at some point in the future. Just to show one of those people, Graham Sherville, who you may know, G3VZV. Graham and I took a visit over to Bochum in Germany a couple of weeks ago. On our way there, we visited ISIS-Space in Delft, picked up some of that flight hardware, and then went on to Bochum to visit our chums at AMSAT-DL and talk about the future GEO opportunity, which is a study being undertaken by ESA at the moment. So if we just have a quick look then, we know what we've got, all that lovely flight hardware, which is worth a small fortune. I think between the 2 projects, AMSAT-UK has spent around €24,000 on those 2 projects at the moment, plus a lot more of payment in kind hardware from ISIS-Space for IP and work done in the past. So what do we need to add to that? Well, we need a linear transponder upgrade. We've obviously got the designs from AO73. They are 6-layer printed circuit boards, and we need to take the latest version of those, which flew on JO97, and give that a bit of an upgrade for the years that have gone on in between. The 23 centimeters FM receiver to VHF transmitter, we're not too worried about that. We've flown 23 centimeters before on the ESA ESEO mission, which was 2019. And we know that although ESEO was a challenge for ESA, our particular part of it did seem to function quite well. So we're confident that that's going to be okay. And we've got an FM capability on JOVIAN-1, so it won't be too difficult to get that particular part of the electronics working. What we do need really from scratch is some work on the camera board with the QSP modulator. I'm aware that Dr. Bridges at Surrey University has done some work on QPSK modulation and can cope with all sorts of wonderful modulation schemes. But we do need to identify a suitable camera that's going to be okay for space and the lens to go with it. People have flown plastic lenses before, and they work for a little while, and then all the plastic begins to migrate off the surface, and you end up with images that look as though you have fog in space, so we've got to be careful about that. We also have a spare slot, on board. We started off looking at a experimental board for digital communications, which I think a while ago we called a mode dynamic transponder. It's going to be an attempt at getting regeneration of a signal on board the satellite, and the idea is that on the ground we can have almost as much power as we like as radio amateurs, so if we can send up a signal that's fairly high in terms of data rate, that's easy to get to the satellite. The satellite can then decode that and remodulate it into a format that's more appropriate for a power-limited system. So, as an example, if you think of 1200 bits per second BPSK up to the satellite, or perhaps slightly faster, decoded on board and then re-encoded in something that's got a much more aggressive forward error correction. I think the most popular application we'll use is maybe FT8 or FT4. So something like that, something that's really good at narrow bandwidth, low signal level reception. So we've got to find somebody, perhaps a group of students, to have a look at that for us. Licensing is another big one. Dave, G4DPZ, has been doing a lot of work with the Civil Aviation Authority in the UK who do space licensing. They've been very, very helpful indeed. And indeed, Ofcom, who manage the frequencies, have also been very supportive. I've said the UK is a hostile environment, and that's particularly true for educational and non-commercial satellites. What I mean by that is the UK government has a requirement for an indemnity insurance in the UK for £60 million. Now, it doesn't matter what satellite you try and launch. It can be something the size of a double-decker bus, or it can be something as innocuous as a pocket cube. But both of those types of satellites, those very different things in size, you still need the same insurance policy for. And to launch a satellite in the UK, those insurance policies will cost you about £30,000 a year, which are annually renewable. And that sort of environment, which is very high cost for people who are not making a profit, explains why, if you look at the license of licensed satellites registered to the UK, you'll find that Professor Martin Sweeting, that we were listening to earlier, had the Eurosat series registered in the mid-1980s, and you can scour through that register and you don't find another UK university registering a satellite until about 2022, 2023. And for education, I think there's nothing better to demonstrate the appalling situation that exists really for space licensing in the UK. So we've got to work around that. We're looking at licensing the satellite elsewhere. AO73 is licensed in the Netherlands, but things in the Netherlands are slowly catching up with the rest of Europe, and it's becoming more and more expensive. We've had some initial conversation about licensing the satellite outside the UK. That's at a very early stage. It's been quite positive, and I think we're on a pathway now to resolving that problem. The launch, well, it's an expensive satellite. All of those parts are worth coming on to £60,000. If you've spent that much money on the satellite, you need a very low-risk launch vehicle. There's lots of people starting up these days. You've got RFA from Germany just about to conduct their first launch from Saxefjord in the Shetlands. We've also got, I think, Orbex, consuming lots and lots of taxpayers' money, building their prime launch vehicle. But so far, I haven't seen much evidence of hardware coming out of that project. Both of those, though, in the early days will be far too high a risk to put a satellite like that on. So if you want reliability, SpaceX is the go-to provider at the moment. We've got a quote for a launch from SpaceX. It's within our budget, so we will probably go for that in the future. Okay, that's about all I can say on FUNcube Plus at the moment. Our immediate priority, though, because of the timeline, is FUNcube Lite on JOVIAN-1. Now, this is a 6U satellite, so considerably larger. So what's that, 30 centimeters by 20 by 10. Still relatively small in satellite terms, but fairly big for a CubeSat. It's a collaboration between 3 universities, University of Surrey, of Portsmouth, and of Southampton, with a payload from AMSAT-UK. As you can see from the representation on the right-hand side, it's got a very large deployable solar panel there, I think the power budget is something like 45 watts, which you can only dream of with a small CubeSat. And that's currently under construction at Surrey Space Centre. If you're wondering why JOVIAN-1, well, the whole project is called Jupiter. It's the Joint Universities Programme for In-Orbit Training, Education and Research. And JOVIAN-1 is simply the first satellite to be built under that educational programme. So JOVIAN-1 then, it's a 6U satellite essentially based on GOMSpace structure and avionics. GOMSpace operate from Denmark. It's 3-axis stabilized, has a single deployable solar panel that we saw in the previous picture. I think that's 90 centimeters, so just under a meter. 45 watts maximum power budget. It's got 5 payloads on board, 4 from universities, 1 from AMSAT-UK. The commercial side of this uses S-band, omnidirectional and high-gain antennas for up and down links, and it's also got X-band fitted for higher speed data. The S and X-band are all commercial frequencies, so X-band in this case is 8 to 8.4 gigahertz rather than our 10 gigahertz allocation, and the satellite uses CAN bus communications. Short project timeline, payload delivery anticipated around December 25. And of course, with all of these commercial projects, you've got paid personnel. And if you have to keep paying people, it eats into the budget. So hence, a very tight timeline to try and get this finished. A little bit more detail, CAD image of JOVIAN-1 here. So we've got an Earth-facing panel on the far side there. It's got patch antennas included on it. It's got 38 solar cells if it's undeployed with that large panel, and 70 solar cells once that panel's deployed. 85 watt-hours storage, and the power supply on it is 8 of those 18650 lithium-ion cells wired in series. So you've got a total of 26 volts at minimum charge and 33 volts when they are all fully charged. So lots of regulation down from that bus voltage. For AMSAT-UK, you can see we've got an antenna on the bottom of this CAD model, a set of UHF antennas here, which is essentially a dipole, with the much longer monopole for 2 meters coming out at the bottom. Ideally, for that monopole to work, we also need the solar panel to come out, because that's the Earth plane, really, that it's going to work with. So it will work without the solar panel, but to get best radiation characteristics, that solar panel does need to deploy. So the payloads then, as I say, there's 4 from universities. We've got a student imaging payload taking still images and video. That's a combined group of students from all 3 universities. There's an experimental proof of concept dark matter detector from Southampton. There's some interesting videos online to describe how that works, with its sheets of graphite floating between a magnetic field and lasers. There's a space radiation monitor, a new design from University of Surrey, and a tiny machine learning payload, or AI if you like, from the University of Portsmouth. And of course, FUNcube Light, which is essentially educational outreach and communications from AMSAT-UK. The ground station at Surrey University has been upgraded. It's a 3-meter dish, and tracking S-band and X-band in low Earth orbit is no easy task. It's a 3-meter diameter dish with 35 dBi gain on S-band. I think that's about a beam width of certainly less than 2 degrees, about 1.5 degrees, something like that. And on X-band, the beam width is going to be absolutely minuscule. So trying to track that satellite as it goes around in low Earth orbit is going to be quite a challenge for the team down at Surrey. The feed, which is down on the bottom right there, has been manufactured in the Netherlands. As you can see, it's two sections of circular waveguide. The inner one is the 8.4 gigahertz, and the outer one is for S-band, or 2 gigs. FUNcube Lite, in terms of its payload, BPSK telemetry, of course. We think that's going to be switched on immediately the satellite's been deployed, because with our ability to take information that's been transmitted over one part of the world, relay it through the internet and have it pop up in Surrey, that will be really useful for the team there during early operations to determine what's going on the satellite before it flies over Surrey. So that's going to be very handy. It'll have its own data coming from the FUNcube Lite payload, but also from JOVIAN-1 via that CAN bus. From a communications perspective, it's got a single-channel FM voice repeater or transponder going from UHF down to VHF. The frequencies have been coordinated by the IARU. It's 435090. Going up with 67 hertz CTCSS and a 10-second timer. And coming down, it's 145895. However, the telemetry and the FM will not be on at the same time. What we anticipate is that initially during the eclipse period, it'll be in FM sort of voice transponder mode, and then in daylight, when the universities are up and about and looking for data, it will be transmitting the BPSK telemetry. As always, we've got autonomous mode change on Eclipse entry and exit, which is very useful for power saving and automatically changing the modes. Windows-based ground station software, telemetry decode and display, and as always, wonderful data warehouse to store things for future use. So mechanical design then, there's a few contradictions in this. The first of which is we've included a radiation detector and then found that we have to put it in a nice big aluminium box, which is probably radiation proof. So, so that's going to be good. We've come up with a 4-board solution based on the standard PC 104 format. So we think we need 4 boards. First of all, a VHF-UHF communications board, a separate VHF power amplifier with the FM transmitter built on it. So there are 2 radio boards, if you like. Then 2 computer-based boards, really, command control and telemetry, and then something that we've called Cannibal, which is the CAN interface board for AMSAT Lite. And to be honest, this is really where we're getting a little bit stuck at the moment, because everyone is struggling to program up the CAN interface on payloads and also program the onboard computer as well to get all those GOM-space parts talking to each other. In addition, we need some antennas, and again, we've nipped off to our chums at ISIS Space for one of their best-selling products. This is the antenna deployment system. It's 98 by 98 by 5 millimeters, and it just bolts onto the external surface of the satellite. If you want to, you can even put solar panels on that, but we don't need to in this case. The elements are folded up. They use some sort of memory metal, and then they deploy one at a time so as not to use too much power from the batteries when the time comes and it's all safely in space. Looking at that module on the back of the satellite here, you can see exactly how thin it is. Just bolts onto the satellite structure, quite neatly fitting in here, and that's just 5 millimeters or so thick. So very, very handy, very, very reliable project, but I think £9,000. So. Okay, won't go through this because we're a bit stuck on time, so if you're watching online via the BATC or on YouTube, the pause button is your friend. I2C communication and some data distribution around our 4 boards with the antenna deployment system on the top left. Looking at some of the boards, we've got the command control and telemetry. This is the one that flew on JO97. The prime component in this is a Xilinx CPLD, and we found that on the many missions that we've run with this design on it, that has never actually failed, which is great. And even if the processors fail, you can still get commands into the satellite, because that does the command decoding and direct communication with the payloads on board. The Freescale processor on there simply gathers telemetry and communicates via I2C to the other boards. So speeding up a little. Cannibal is the new board on there. This is an STM32 processor running at 170 megahertz as a CAN interface. It does CAN to I2C conversion. It's got the BG51 radiation detector on the bottom left-hand side there, because we have plenty of space on that board. And then we've surrounded it with aluminium, so that'll be interesting. And top right-hand side there is a switch mode power supply to convert the 32 volts or so down to 8.6 volts for our VHF PA. The transponder board, UHF receiver, and the control logic for the sort of repeater and telemetry generation is done on this board. I think there's about 300 components on that, all told. And finally, the VHF amplifier board, which is a development from the original AO73 one, which is very, very reliable. We've added a driver transistor to that, so it needs about 0 dBm for half a watt out. It's got some sensors on board for PA temperature, forward RF power, reverse RF power, and supply current. And it's got a combiner on board, so we can feed that with 3 separate inputs without actually having to rely on a switch, which might be unreliable. On the reverse side of that, probably the smallest FM transmitter you'll come across, just a single device from Silicon Labs. An SI550 VCXO. It's essentially a microwave oscillator with a whole bunch of DSP inside it. Works reasonably well. The price for having a very small device count is you get a little bit of phase noise, which you can see in the middle of the photo, but it's acceptable. It's still about 45 or 50 dB down. And as with all things, you can test forever in a lab, come up with nice graphs. This is the linearity of the amplifier. But really, as we are radio amateurs, it's good to take the boards you've assembled, stack them together, put them in the back of a car, replace a complicated computer with a few switches, drive it to the top of a hill, and actually have a few QSOs through it. So I drove this up to Dunstable Downs in Bedfordshire. We managed to get it working over about 60 kilometers with 150 dB path loss, and there were some QSOs using the hardware that's going to be put together for this project. Surrey Space Centre started off, whole pile of boxes around the room there with the GOM-space structure in the foreground. Once unpacked, slotted into the bottom part of the structure there, and all the CAN IDs being programmed into it. And then somebody else in the audience here standing around doing some vibration testing on a pod, which the satellite is going to go into. And finally, a picture of our antenna system and a few more things being loaded into the structure. Okay, so rather rapid. But that's a project update on FUNcube Plus and FUNcube Lite on JOVIAN-1. Thank you.
Thank you, David. And if anybody wants to see an example of something that looks like a CubeSat, we have a 1U demonstrator on the AMSAT stand in the special interest group area. It's actually the AMSAT North America CubeSat sim, which is actually transmitting telemetry. So if you want to pop down, we can give you a talk. We can give you a demonstration of that. And while I'm on that subject, we're running a QO100 live station as well. Many thanks, David. Are there any questions?
David, one question I've got is obviously you're using UV. Why not VU? Is this to do with allocations?
Okay, so the question is, why are we using UV and not VU? The answer is there's less path loss on V-band. So if we ran a U-band transmitter on the CubeSat, we'd have to run more power to actually get the same signal back down here on the ground. So U uplink, you can generate as much power as you want. VHF on the satellite is by far the most effective because it's less power to get the same signal down on the ground.
Hello, a question about FUNcube Lite. Will be able to operate independently from the main satellite? How much freedom you have there?
Okay, the amount of freedom is based on really our responsibility to the regulators. We would like to have it permanently connected to the power supply so that we can command it on and off ourselves. That's not possible. And so we are a payload that is switched from the main satellite. Okay, I think that's it. Have a nice belated coffee, and thanks for turning up here rather than Lucy Green, who I have every intention of watching on YouTube later on. Thank you.